Good morning, AP Physics. I'm glad you slept in. Sorry we missed you, especially 2 days in a row. And being that we need to get rolling, I thought I would help you by making a video. Basically, we're just going to take some more of our linear information that we already know and apply it to circles again, just like we did in the last chapter. In fact, here's a start on it. We know that force, we've been dealing with that since Physics A, has a letter F and we measured in newtons. The circular counterpart of force is called torque. And of course they have a Greek letter for this called tau. And for reasons we'll talk about in a minute, it's measured in Newton meters. A lot like work is, but you can't use joules, and we'll talk about why. You can exert torque on things. In fact, it takes torque to make this wheel move around and around and around. And it turns out you can't push this way to make the wheel rotate. You have to push at least partly sideways, or let's say perpendicular to the radius of the wheel. That's how you make things rotate, by exerting torques. So this is what I would be doing on the wheel. I would be pushing this way, and that makes the wheel rotate. In fact, we'll find out later on the only reason that a wheel like that rolls on the ground is because of a backwards frictional force that actually makes the wheel rotate. And so torques have a big part in our everyday lives. Imagine a big kid and a small kid sitting on a seesaw. In fact, this kid is trying to make the seesaw rotate this way, which we call a negative torque. So just like our unit circle, angles this way are positive, torques this way are positive, and torques that are clockwise are considered negative. This little kid is exerting a positive torque, counterclockwise. This kid's exerting a negative torque clockwise. And you can see what happens. This kid exerts a small force because it doesn't weigh very much, but they're further from the axis of rotation. That's what R stands for. The big kid exerts a much bigger force because they have more mass, more weight, but they are lots closer to the axis of rotation. The axis of rotation would be the fulcrum. And so some people say those are balanced torques, and some people would write it this way because they're actually adding a positive torque plus a negative torque. Either way, if the kids aren't rotating this thing, then the net torque must be zero, and that's how you write that. You exert torques every day in your life when you try to open a door. So this is an overhead view of the door. We're up on top of the door looking down on the top from it. Like, these are the hinges. There's a handle in there somewhere. And you can push on the door, exerting a torque. And again, here's the axis of rotation, right? The axis of rotation is here. You're exerting that torque perpendicular to a radius along the axis. You could also pull on the door. And again, most people pull this way. So you would be exerting a torque. In fact, this would be a negative torque. And how much torque you exert depends on, again, how hard you pull and how far you are from where that thing rotates. Now, some things you could do, you could pull this way, not completely perpendicular to the door. There's no problem with that. It turns out that it's not as effective. You could also pull this way rather than completely perpendicular to the door. And what happens is only part of that force matters, only a component of that force. So if you do decide to pull this way, and you break that force into two components, as we've done many, many times, only this component of the force actually exerts any torque. If you push this way on a door, right along the door, that is just like trying to make this thing rotate by pushing like this, and it simply doesn't work. So at the end of a door, you don't push on it, and if you do pull or push at any kind of angle, only the component that happens to be perpendicular to the object counts. And that's why the formula is often written like this. Your formula page might even have a sine of theta kind of thing in there. I wouldn't memorize that. All I would do is try to figure out which piece is actually perpendicular. Look at it and ask you what part of it is actually making things rotate. In fact, when you get into some of the homework problems, one of them asks you about a pendulum, and so this is the string and this is the pendulum itself. Well, a downward gravitational force does make this thing rotate, or actually revolve. But in this particular instant, this component of the force isn't providing any torque whatsoever. It's awful hard to make a pendulum rotate by pulling this way on it. Instead, only this component at that particular instant actually is providing any torque and making it rotate or actually revolve. There's another question about trying to extract a tooth in the homework in question number 3, and the axis is like this, but they're pushing like this. Well, similarly, this component doesn't provide any torque at all. Only this component, which happens to be perpendicular to the tooth, actually provides a torque. And again, that's why the formula is what it is. It's measured in Newton meters because we're multiplying some sort of force, sometimes some kind of distance. In the English units, you'll actually hear them talk about foot-pounds, which is sort of backwards, but that's the American equivalent. And so torques are used all the time to make things rotate or revolve. Likewise, you could look at it sideways, I suppose, and pretend this is a merry-go-round, and you have to grab onto the handle of a merry-go-round to make it rotate like that. That's a good example of torque. And you couldn't do so by either pulling out or pushing in. You have to do something perpendicular. And that's another example of how torque is used in your everyday life. As long as we're talking about linear equivalence and circular equivalence, we can go back to Newton's first law, which says if you have balanced force, you don't get any acceleration. And we didn't say no movement, we just said it doesn't speed up or slow down. And the circular counterpart says if you have balanced torques, you don't get any angular acceleration. And here would be one example. If these two are not moving, then the torques are balanced. Now, even if they're moving very, very slowly, but at a constant rate, those are still balanced torques. Because balanced torques doesn't say nothing moves, it says nothing speeds up or slows down. So balanced torques can't cause something to spin faster and faster and faster or more slowly. They can simply keep the rate where it was before, which might be 0, or it might be moving. And so here's Newton's first law. Acceleration is given by net force divided by mass. Similarly, here's the counterpart for angular acceleration. And here's the counterpart here. What we need is a counterpart for what do you put in for mass. Because when you're pushing on an object, its shape, what it's made out of, really doesn't matter. Only the mass itself matters, regardless of the shape. But it turns out when you're trying to rotate something, where that mass is concentrated makes a big difference. We've all seen a skater spinning in a circle, and they bring their arms in and they spin faster and faster and faster. That skater has not changed their mass, I hope, by bringing their arms in, but they have changed where that mass is. And what they've done is effectively concentrated their mass closer to the center, and it turns out that that makes things easier to spin. And so we would have to fill this in with something that is like mass, but that also takes into account where the mass is. And what they've come up with is capital letter I, which is not, it has nothing to do with current like it does in electricity. It's called rotational inertia, which makes sense because this is inertia, this is rotational inertia. And it is basically something to do with the mass, and it has an R squared in it, where the R stands for, on average, how far is the mass from the center. So when I spread my arms out like this, on average my mass is further from the center. When I bring my arms in, the mass itself didn't change, but on average where that mass is does change. In fact, you can tell the fact that it's squared means that it counts a lot more than just the mass itself. So here's some examples. If this is a pendulum, and we're just talking about the pendulum itself swinging back and forth, well, then all of the mass, if we disregard the string, all of the mass is located out at the very edge, and the angular inertia, or rotational inertia, would be mr squared. Likewise, sort of like the bicycle tire, this isn't quite true, but it's close. Almost all of the mass is out of the edges. The spokes don't have a whole lot of mass, so this wouldn't quite be true, but it would be close. If all of the mass is at the edge, like a hoop or a ring, then again, you could use mr squared as a formula for the rotational inertia because all of the mass is at the outside. If you have a disk, though, where it's filled, then all of the mass is not out of the edges. Some of it's in here, too, and it turns out that the fraction in front just changes. And this fraction, all it does is give us an indication, on average, how far is the mass from the center of rotation. If you take this is a disk, this is supposed to represent a ball, so it's supposed to be a three-dimensional picture, and we all know what a ball looks like. The fraction in front is even different. It just says that on average, this mass is even closer to the center than a hoop or a disk either one is. And that's all those fractions do, is they tell you on average how far is the mass from the center of rotation. If you had a baton, let's say, where most of the mass is at the edges, right, the baton's more floated up in the air, most of the mass is at the edges, but there is some mass in here. I would imagine that that fraction would be something like 0.7 or 0.8, because not all the mass is at the outsides, but there is some here on the stick itself. In fact, you take just a stick and rotate it about its center, on average the mass is not all that far away from the center. But if you take a stick and try to rotate it from the end instead, you can tell that on average the mass is much further from the center of rotation. So a lot of counterparts. Again, balanced forces don't cause things to speed up or slow down. Balanced torques don't cause things to rotate any faster or slower. Here's a nice one. We're used to that one. This should be a pretty easy counterpart for you to follow. It's just going to take a little bit of time to get used to this. So again, rotational inertia or angular inertia have both used. And it's always something with mr squared, but there's always going to be some sort of fraction in there that indicates how closely the mass is, on average, to the center of rotation. Because it's our second snow day in a row, I need you to do something. I'm trying to get this video to you before 10 o'clock in the morning. I'd like you to try 1, 2, 3, 4, 5, 6 problems out of chapter 8. So 1, 2, 3, 5, 24, and 26. Those shouldn't take all that long. And I would appreciate if you do that so that when we come in, we're ready to go. And I hope to see you tomorrow. Thanks.